All right. Okay. Yeah. Thank you very much for inviting me to this session. Um, my presentation is called Let's Rock Biochar, how mineral doping of biochar might provide multiple benefits for carbon management and soil properties in agriculture. And this is a project called PIMAX, taking place at the University of Hamburg, but also in cooperation with the Hochschule Geisenheim and the Potsdam Institute for Climate Change Impact Research, and in close cooperation with the Ithaca Institute in Germany, our Biochar Institute. And PIMAX is a part of CDR Terra. CDR Terra is a big research initiative to research all possible carbon dioxide removal methodologies on land, on the terrestrial part. And to introduce myself, I'm originally from marine geology and biogeochemistry. So I love rocks, and this is what why I'm doing mainly. And I was also a polar researcher during my PhD, and I do a lot of science communication as well. And currently I'm working in CDR Terra, CDR Mare, and I'm involved in the Carbon Drawdown Initiative that does enhanced weathering in a greenhouse, in the Catalyst program of Carbon Future, and advising at InPlanet. So the project name is called PIMIX, which is a combination of Pi, Me, and CCS. So CCS is standing for carbon capture and storage, of course, and Pi is also something that you all know. Pi is standing for pyrogenic carbon. So the process here is pyrolysis to generate a stable organic carbon form, which we call biochar. Yeah, and I think you are all familiar with the process. Like we have the input of biomass, the pyrolysis, the harvest of different products like gas, liquid, and the biochar, the heat as well. And it can be used for soil improvement, as it was done in the tropics for a long time. And the Me in the project name, the PIMIX, is standing for mineral weathering. The process here of the carbon transformation is the weathering of rock, and the product is a stable inorganic carbon that is mainly realized through, or the weathering process itself happens when a mineral is mixing with water and CO2. So water and CO2 can form a weak acid, the carbonic acid, with each other, and they attack the mineral structure. The products from this are dissolved cations, silicic acid, and bicarbonate. And bicarbonate, that's quite funny, that's a natural component of mineral water. So we drink it every day without realizing that we're drinking stable inorganic carbon. I'm saying this because some people believed for a long time that this kind of bicarbonate could be harmful or toxic, but it's not. So you're all familiar with biochar, but not with mineral weathering, I guess. So I will concentrate on explaining you what mineral weathering is and how it works. And if you look on a rock, for example, the basalt, one of our favorite rocks to weather, you find different groups of minerals in this rock. For example, the pyroxene group, the plagioclase group, and the olivine group. And within these groups, you have different minerals. That means every mineral has a very specific chemical composition, a very specific crystal structure and properties. And every mineral, of course, weathers in a little bit different way, like the others, and can sequester more or less carbon than other minerals. I take one example right now, our superstar in the olivine group, that's the green one here. It's called forsterite, and it has a very, very simple structure, is weathering relatively fast, and can sequester a lot of carbon compared to the weight of the mineral. So in the following, I will explain a chemical equation, and I think most of you are familiar with chemistry. For those who are not, don't panic, because chemistry is nothing else like swapping partners. Just imagine the molecules are relationships, and sometimes relationships break apart and they change partners. So imagine that our foster right is going out for a party and is going on a dance floor. And on this dance floor, the foster right meets 4 molecules of water and 4 molecules of carbon dioxide. They have a lot of beer they haven't seen for a long time, and it happens that suddenly magnesium becomes single. Why? Well, the silicate is having an affair with the hydrogen, because hydrogen is in the media a lot recently and seems to be very sexy. And water and carbon dioxide, they form bicarbonate because this is an old love that they revive. But in the following, you all know that on the party there's 1 hour where some romantic music hits the dance floor, and everybody is looking for the next partner for the next few years. And also magnesium is falling in love again and asking carbon and oxygen, do you want to move together with me? And they are overwhelmed and they form a mineral called magnesite. And the special thing about magnesite is this is a love that lasts several thousands of years. Silicate is a bit disappointed by the hydrogen and is now sticking on their own. They form, so silicate and oxygen, they form opal. This is also a mineral. And water and carbon dioxide, they go to the next bar to see what minerals they need over there. And this seems to be very, very complicated, but you don't have to remember this. The only important thing on this big party night of the molecules is that one. So at the beginning of the party, you had 4 carbon dioxide molecules. At the end, just 2 go home. So 2 have disappeared. And this is because in the first step, which is the weathering, the carbon dioxide was transformed into stable inorganic carbon, the bicarbonate. This molecule is dissolved in water and can stay wherever you have water bodies like the groundwater, rivers, or the ocean. And in the second step, the mineralization, half of the carbon became a solid mineral that can be magnesite, but this can also be calcium carbonate, forming, for example, corals and shells and so on. So this is the very simple scheme of how mineral weathering works. When we put this if we put these minerals in the soil, many more things happen. So first of all, we don't have just phosphorite, we have many other different minerals that interact with water and carbon dioxide. In consequence, we have more than just magnesium. We have aluminium, iron, calcium, magnesium, potassium released, which can act as plant nutrients. The silicic acid that is forming is supporting the clay formation in the soil. So if your soil is not rich in clay and can benefit from clay formation, this is quite a good thing. And the bicarbonate is normally transported to the ocean. The ocean has a huge capacity to hold bicarbonate for 100,000 years. And if mineralization takes place, then it mainly ends up in marine sediments or shells and corals and so on. And we do this enhanced weathering, or it's called enhanced weathering, when we take volcanic rock, we grind it to powder, put it in the soil. And there are lots of benefits in the soil because through the plant respiration, the root respiration, we have higher CO2 levels in the soil. We have also microbial and fungi activity that mix the soil and allow more water and carbon dioxide to reach the minerals. And we have a constant humidity, or very often a humidity, which is necessary to let this reaction happen. So in our project, we have on the one side pyrogenic carbon, which has lots of benefits for the soil. And on the other side, we have the mineral weathering, also providing lots of benefits for the soil. And our idea was, okay, what happens if we mix both together? Can we, do we have any interaction between those 2 species? And can they push themselves a little bit more, maybe for a higher carbon sequestration? And another idea in that project that we're testing is what happens if we make mineral doping. That means before pyrolysis, the biomass is mixed with a mineral, and then both is pyrolyzed together. So they are pelletized before. And the big question is what happens during pyrolysis and how are the properties different from normal biochar? Is there a benefit in that method or not? So the first step, so just mixing pyrogenic carbon and mineral weathering together seems to provide a lots of benefits. So this is an overview from a study based on what do we know already about both methods and how could they act together. So these are some suggestions that from property benefits that a soil can get from the co-deployment of biochar and minerals. For example, both increase the nutrient pool and the biochar optimizes the soil hydrology. The soil hydrology is important for enhanced weathering to take place. On the other side, if you have fine-grained minerals, you have a much or a bit better water holding capacity in the soil as well. Both of them stabilize the soil pH, and biochar is increasing soil organic carbon, but also the formation of clay humus complexes, for example, or just the bonding of minerals to organic particles can also stabilize and increase the soil organic carbon. So this is what we think. It has also been shown in mineral-rich soils that biochar can get something like a calcium coating, and little minerals fill and seal cracks in the biochar when it is getting degraded, and a negative priming can happen. So in the biochar is getting more and more resistant against microbial activity. And yeah, there's also the chance for the formations of aggregation, mineral-associated organic matter can form, and a cation bridging can appear. So this is what we expect for the simple co-deployment of both. With the doping, so the doping, first, the biomass can be mixed with minerals, but it can also be soaked, for example, in a solution, or it can you can spray on something that you have, like a fertilizer or so. And from this very, very good review study from Bus et al., where you find every information you need on that topic, it is suggested that this doped kind of biochar would produce a higher carbon yield, also a higher yield in biochar itself, because you added several kilograms of minerals. If, for example, if you have 10 kilograms of biomass and you add 2 kilograms of minerals, these 2 kilograms of minerals, they will stay, they will be there after the pyrolysis as well, because they don't evaporate in any kind. So at the end, your biomass has shrunken, but the minerals are still there. So the total mass of biochar might be higher, or is higher. And this leads to the fact that you might need less biomass to produce the same weight of biochar, and this could lead to lower costs. Yeah, so we have ongoing experiments right now, as you can see. Here in the corner, my colleague and I, we built this, or we're maintaining these boxes. In these boxes, we have columns where we mix soil and different kind of these mineral doped biochars together, but also biochar and minerals as a co-deployment. And within the boxes, we create an elevated CO2 concentration to simulate the higher CO2 concentrations like as you find in real soils. But we also have such greenhouse experiments that are not taking place in our university, but they just have started a few months ago. And we have, we have three different kind of soils, three different kinds of doped biochars, but also normal biochars. And for us, as we work with, or as we come from enhanced weathering, it's very important to see what cations and what minerals are dissolved in the water that we put on these columns. So we harvest that water that is coming out of the columns every few weeks. And based on the chemical composition, we can estimate the carbon sequestration potential and also the potential of nutrient release, for example. In summary, I think I was very fast. But yeah, in summary, we know that both mineral doping, but also the simple co-deployment could provide several benefits for the soil. For example, creating higher or stable carbon yield, higher biochar yield, maybe impact the nutrient management. So it was seen that if you have a phosphorus-rich biomass and you add potassium to it, then you create potassium phosphates, which are highly dissolvable and therefore very good available for plant roots. But as we are not working with phosphate-rich biomass, this is not relevant for us, but this might be relevant for others. We hope to also support plant growth with it and to increase the carbon dioxide removal potential with that. And from the pure co-deployment, we also hope to have something like a priming effect and increase the improved soil hydrology and see difference in the soil pH and so on. And also we hope for a faster enhanced weathering because we have more humidity that is in the soil. But in one experiment, we could already see that we had a very clayey soil, and our soil columns were blocked, so the rain was not going through anymore. But in all columns where we had biochar, the biochar helped to drain the rain through the column, and we could let it rain all through the experiment through. And so we saw that if you have biochar in a very sticky soil, we have the chance that rainwater is draining, although the high clay content prevents the draining. And another thing that we have on mind and that we want to prove in our project, or not proof, but an idea that we want to develop is that the co-deployment of pyrogenic carbon and mineral weathering is very nice to create a complementary CDR portfolio. So this is adapted from the Ithaca Institute, this graph here. So the fact is that if you put biochar in the soil, you have sequestered a certain amount of carbon dioxide right at the first day. Over time, you have the dissolving of the labile part, but the stable part stays, of course. But over the time, your sequestered CO2 is shrinking a little bit. With enhanced weathering, it's the opposite. So on the day you put minerals in the soil, you have not no CO2 sequestered at all. It comes over time when the weathering process is progressing more and more and more. So, and as the sequestered carbon from the biochar is slowly fading away, you have a growth of the CO2 sequestration from enhanced weathering. And this is what this graph shows here. Like, it is a little bit of too much label part, I would say here, but you have the sinking or the shrinking of the C sink from biochar and the growing of the ceasing of the enhanced weathering. And from this, you can guarantee like 1,000 kilograms of CO2 sequestered over a long time. Yeah, I was very fast. Sorry. So our experiments are still going on. We have about 2 years more to harvest data and publish them. So you will definitely hear something in the next 2 years from us. I really recommend to follow the idea to mix different carbon dioxide removal together, because we can have a lot of benefits of it. Also, if we, for example, combine it with then bioenergy plants on top, so we have an even higher CO2 sequestration potential on one area. You can get the newsletter from CDR Terra to stay up. I think it's also available in English. You find me on LinkedIn, and these 3 papers here are the most important. I really recommend them to you if you're interested in that topic. And there's also one tip from me. I made a different kind of science story, how biochar and rock are interacting together. So if you're interested in a bit more input. Yeah, that was it.
Thank you very much, Maria, for this very nice and entertaining presentation. So we don't have a lot of music usually. And I'm very interested in what you're working on, especially because I've worked with Wolfram Bus on the publication you mentioned. My question would be, so what kind of minerals did you use in your experiments?
Yeah, so we usually work with a basalt or a basanite. That's a volcanic rock that you can find here in Germany, and it's sold called Eifel gold. Mm-hmm. And yeah, you can also you find it in every city. You can buy it. You can buy it to fertilize your garden plants.
So okay, it has a fertilization effect. So, yeah. Okay. So then you got, so if anyone wants to ask any questions, please write them into the chat or unmute yourself, which you can now do, and probably raise your hand up front. So Marshall was asking a question, can this be deployed at scale, or, yeah, that's the first question.
Yeah, good question. I think it can deploy. So the co-deployment, I think, is much more simpler, because you just throw the biochar on the field and then you throw the minerals on the field, or the other way around. It's just about mixing them. I think, for example, if you look to India, you have a lot of resources of these kind of rocks. So I think the whole Indian continent is just covered in volcanic ash, and which you can use for enhanced weathering. And if you combine it with biochar, it would be very easy. The mineral doping seems to be a bit more complicated, because I already tried to pelletize myself the biomass with the minerals, and it was really, really challenging. And yeah, I think you have, there are companies that make the pellets for you, but you need huge amounts of it. And I think this is a little bit of a technologically challenge still. And yeah, so enhanced weathering could scale, I guess, easily, but we're having still challenges how to measure exactly the carbon drawdown, because the release of cations in the soil and the formation of bicarbonate is overprinted by many other signals in the soil, like microorganisms or rain and evaporation cycles and so on. So at the moment, we don't have a cheap and scalable method to measure the enhanced weathering out on the field. There are a few very expensive methods, but they don't scale. Yeah.
Okay, so potential, but not yet.
Yeah. And I think the global potential, so the carbon sequestration potential for enhanced weathering is somewhere between 3 and 5 gigatons per year if you have it on global scales.
So a bit bigger than what Biochar is, if I remember correct. So Sean Thomas was asking a similar question, or one that fits a bit. Grinding minerals is energy intensive. Could one use specific types of mine tailings that are already fine particles?
Yes, that's a very good question. So often when rock is crushed, you generate powder or dust that is catched in filters. So you can use the powder from filters, that is waste. Mine tailings can also be used. The rock needs to be ultramafic or mafic. This is a specific composition of the rock chemistry. But there was just a very nice research project called Details in Spain investigating this. And I think Liam Bullock was doing this. And he also had a very nice publication on the potential of mine tailings for enhanced weathering. In general, it makes sense to use waste streams, also like you do on biochar, for enhanced rock weathering, and not just mining the rock because you want to weather it.
Is it?
There's also a company using crushed concrete that you can also use.
Just out of curiosity, is there any regulation so far on mineral weathering on the application in soil in terms of heavy metals or aluminium?
Yeah, it depends. In Europe, if you use it as a mineral fertilizer, it falls under the European regulation for fertilizers, and then you have some limits of trace metals. So the green mineral I showed you in the presentation is normally very high in nickel and chromium, and the rock that is containing 90% of this mineral, it's called dunite. For example, this would not be suitable, or this would not be legal to be spread under this law. But the rock that we use has lower concentrations of trace metals, and then it's not a problem. It's already legalized as a fertilizer.
So now I have to jump through the questions. So John Hoffmeyer was asking, phosphate deposits in South Africa include cores of pyroxenite. Is that a mineral somehow related to pyroxene that you referred to early in your presentation? If you know that, I have no idea. Pyroxenite.
Pyroxenite. It sounds like, yeah. I don't know this mineral, but I would say yes, or maybe you can Google this very easy, and then you find the information, like to which mineral group does it belong. But sometimes you have minerals that weather, but they really not sequestered a lot of CO2. So, yeah.
Sorry, I'm trying to quickly go through that now. Markus Schiedung was asking, do you conduct all the experiments with temperate soils or in temperate conditions? First question. And the second follow-up question, another question would be about the availability of suitable basalt to scale up on a meaningful scale for carbon capture. You already answered that one, but do you conduct all the experiments with temperate soils and under temperate conditions?
Yeah, we do it in a room that is has a very small temperature range of between 15 and 22 degree. This is challenging. And in the greenhouse or the field experiments, we have a bigger temperature range, of course. And temperature is also a big impact on enhanced weathering, of course, yeah. But in our lab studies, which are highly controlled, we have this like very small temperature window.
And Karuna was asking, when we modified biochar with minerals, so metal salts, they make the biochar surface positively charged. No, wait, that was a question. Are they then positively charged when you modify biochar with minerals, the surface? So do you change the surface charge after doping?
I don't really understand. So
I think he or she means that after doping before pyrolysis, you will most likely change the biochar surface charge to a positive charge due to the mineral introduction.
Yeah.
Did you see that?
The doping is you take the unpyrolysed biomass and mix it with something, and then during pyrolysis, I really don't know. I just can say that the ability to take up water is more or less the same from the doped biochar. We haven't tested this, or we will find out. Yeah, this is a good point. We will find it out.
Okay, and he or she mentioned that this could be used for the removal of anionic pollutants like phosphate or nitrate from water. And the last question from a smartphone, apparently, Mutabara. Rock properties changes depending on pre and post doping. How are you managing it? And I tried to rephrase it a bit. Do you think that the minerals dissolve similar after they are pyrolyzed with biomass? Or do you expect changes in the dissolution rates?
Yeah, so the rocks, they are used to temperatures like 1,000 or 1,500 degrees. So we pyrolyzed them at 650 degrees. This should not change the rocks, but we expect them to weather faster, maybe, because the single minerals could have get some cracks through the heat or the heating, and at the same time, when the biochar is holding more water, which and the biochar is located next to a mineral, then the mineral is in contact with water, and then the weathering can take place.